Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about the petroleum fractionation column that is used in the refinery processes, how we can do it in Aspen Plus. We all know how a distillation column works. The distillation is a separation process by which we typically separate two or more components based on their boiling points, provided those boiling points are distinct enough. Okay? Say a binary distillation column where we have a distillation column like this, and the mixture that enters into the column, they typically have two components, and one of them we call light key and the other one is called the heavy key components. Light key means it has lower boiling point and the heavy key has higher boiling point. So as we increase the temperature of the mixture, then the light key components, they start boiling first and they tend to go higher in the column. There we have a provision of a condenser, and this condenser condenses the liquid. Majority of the liquid is sent back into the system and some portion comes out as distillate. And this distillate typically has more amount of this light key component and less amount of heavy key component. On the other hand, the heavy key component tends to go down the column, and here also we have something called reboiler, and the reboiler heats up the mixture over here, and majority of the mixture is sent back to the column and some portion is taken out, and this portion is called the bottom product, and this bottom product typically has higher amount of heavy key component and very little amount of light key component. That's how the light key component and heavy key components are separated through a distillation column that we all know how it works. Even if we have more than two components, that is multi-component mixture, we may have component 1, component 2, component 3 and up to component n. So if we have n number of components in a multi-component mixture, that also can be distilled provided the components have distinct boiling points. Okay? And then it can be sent to a multi-component distillation column, and each and every component can be separated as per our requirement. So Aspen Plus has the option for multi-component distillation column. It has the option for binary distillation column, which you already have learned, but it also has a provision for crude distillation, that is the petroleum crude, which can be fractionated in products like C1, C2, C3 up to higher hydrocarbon components. So Aspen Plus has the option for crude fractionation. It has a dedicated unit called Petrofrac that we can use, provided we have correct information of the crude or petroleum assay or blend that we generally term it as. Now let us go to the Aspen domain and see what we have to do over there. So in Aspen Plus, you will find something called assay or blend. So this is used to define the petroleum assay or crude assay or crude blend. How it is done, we will learn later. And once we define our crude along with the components that it has, we can do the petrocharacterization. And this petrocharacterization is needed in order to do the petroleum fractionation and to run the petrofrac column later. This is about the blend. First, we have to define a new blend, and that blend can be the type assay or blend. And once it comes over here, there are various options of distillation curve. As we might know that the crude oil, it doesn't have any single boiling point component. It's a mixture of various components that has wide range of boiling points. And those components, they have boiling points, they are very, very close to each other. For instance, suppose you have some crude oil, you start increasing its temperature and some amount of volume fraction will be distilled. If you further increase the temperature, some more amount of volume fraction will be distilled. So if you say this is 5% volume fraction, it will be reached up to say 20 degrees centigrade. And then 10% volume fraction, it reaches 43 degree centigrade. Then 20%, it reaches some 70 degrees centigrade, and so on. So if you plot this data, you will find a curve which looks like this. So this is called the distillation curve. Okay. So this distillation curve is very important for characterizing the petrochemical product or blend. Okay. So we have to provide the data in terms of the distillation curve type. Now there are various types of distillation curve. ASTM D86, ASTM D1160, true boiling point based on liquid volume basis, true boiling point based on weight basis, and there are options for vacuum distillation also. Now those who work in petroleum refining industry, they know what they are. What means ASTM D86, ASTM D1160. Basically, they are the standard types of finding the distillation curve. Okay. So people who already know this, you know what to do with them. And those who do not know what they are, you can read through any standard book. You will find enough information about it. So what you need to give is, you need to provide either the specific gravity information or API gravity information and the percent distilled amount that you have to give. Say, you say 5% distilled at what temperature? It may be having, say, 56 degrees centigrade. For 10% distillation, you may get at 70 degrees centigrade, and so on. You can go up to 100% like that. So this information that you have to provide over here. And then you have to provide the information of light ends. Light end means the lightest amount of component which will go at the top. Okay, so what is the fraction of the light end and what are the components? You have to do the analysis of the light end components. Say methane. Methane will be this much, the mole fraction or mass fraction of methane. How much is ethane? How much is propane? How much is isobutane? How much is N-butane? And so on. And what will be the higher components? So those information you have to provide over here. And also you have to provide the property curves based on the information that you have. For instance, you may have the information of flash point of that petroleum mixture. That you can give, say, the flash point. If you choose this one, then what is the flash point of petroleum mixture at 5% distilled? So that value you can provide over here. So at 5%, what is the flash point in degree centigrade? At 10%, what is the flash point in degree centigrade? So those information you can provide over here. Similarly, if you choose, say, smoke point, that also you can provide what is the smoke point at 5% distilled. What is the smoke point at 20% distilled? So that information you have to provide. Okay. And then their light and properties. I mean, you provide those information of flash point or smoke point or freezing point not only for the petroleum mixture but also for the lightened components. Okay. So lightened properties also may be given over here. And then after you provide this information, you have to perform the petrocharacterization. In petrocharacterization, first you have to provide for which component you need to do the petrocharacterization, which blend or which crude. So that you have to bring in over here and perform the analysis. Okay. So until unless I provide you with an example, this will not be clear to you. So for the time being, hold your understanding over here. Let us go to the simulation. So once you do this petrocharacterization, you have to go to the simulation, and the simulation you will find the columns over here. So here you can see this is multi-frac. So rigorous fractionation for complex columns such as crude oil. So this is for multi-component distillation, multi-frac. And there is SC-frac, that is shortcut distillation for complex columns such as crude units and vacuum towers, both. So this is shortcut distillation. Today, we will discuss about the petrofrac. The petrofrac is rigorous fractionation for petroleum refining applications such as pre-flash towers, etc. Okay, so this we will use today. Now in petrofrac, if you take it over here, do not get confused with icons like this. There are a lot of other icons. You can use a simpler icon of this nature also. It doesn't matter. You have to understand what exactly it means. Basically, you have a main column feed. Here you have vapor distillate. Here you have liquid distillate. And here you have the bottom product. And there are other outlets and inlets also. Here you can provide the steam for steam distillation. Option is there. Here there is a furnace. I mean, you can always say that I will not use a reboiler, I will use a furnace which heats up my feed before it is entering into the column. And these are typically the strippers. Okay. So in the petroleum fractionation, you do not fractionate only at the top and the bottom. Rather, you may say that I want to extract the light gas oil or the kerosene or the heavy naphtha or light naphtha. So those are the different fractions that I want to extract from the distillation column. So it has given the option to use separate strippers in order to extract those extra streams out of the column. Okay. And there are other options like pump around. I mean, pump around means you take out some heat from the column so that the condenser doesn't have much of a load. Okay. So these pump arounds are required to extract the extra heat, and that way the stripping occurs in a better manner. So all these things we will learn today. Typically, in this block, you will find we have to provide certain data, the stream, pressure. These are the two things, pump around and strippers, that we will learn. Okay. Now, in order to understand it in detail, let us see the example. Now, the example says a crude oil assay with bulk specific gravity. So this information is needed. Bulk specific gravity of 0.85 is to be processed in a refinery. The TBP distillation curve, TBP means the true boiling point distillation curve of the crude is given. Typically, this true boiling point information is obtained through experiments. Okay, so they have given 5% volume distilled is obtained at 60 degrees centigrade. 10% volume distilled is obtained at 115 degrees centigrade. 20% is obtained at 180 degrees centigrade, and so on. Ultimately, when we reach 830 degrees centigrade, then 100% can be distilled. So that's what it means. The total fraction of light ends is 0.00352. So that is the light end fraction that goes at the top. Okay. So that is the light end fraction, and its composition is also given. What are those composition? We have methane, ethane, propane, isobutane, N-butane, isopentane, N-pentane, and also some higher hydrocarbons. And there will be negligible amount of CO2, N2, and H2S. So they are the components in the light ends. Okay. But you will find the majority of the components are propane and N-butane. N-butane almost 1/3 and propane is 1/4. Okay, rest of the things are there. And what we need to do is we need to provide the petroleum assay characterization, and we have to generate pseudo components. Pseudo component means basically what we do, we know that we have a standard distillation curve of this nature. Okay, so we have different cuts, right? And this cut, say it is 10% to 20% distilled curve cut. Now they have a range of boiling point, right? So they basically do not have a fixed boiling point. They do not have fixed molecular weight. They do not have fixed viscosity, API gravity, specific gravity, etc. Because they are combination of various components which we cannot distinguish. Okay, so they are basically cuts, and all those cuts we call pseudo components because they are not exactly a specific component like methane, ethane. Okay, methane, it has a fixed molecular weight, right? It has an own identity as methane, right? If you say methane, we know it is CH4, right? So the pseudo components, that means if it is a mixture of everything within that cut range, it doesn't have a specific identity of its own. So we call it a pseudo component. So we have to generate a list of pseudo components first. And once we do it, we go to the next part of the problem that says that 350 tons of this crude oil is processed in the crude oil primary distillation unit, consisting of an atmospheric distillation column and a vacuum distillation column in series. So both atmospheric column and vacuum distillation column are there. The feed enters the unit at 170 degrees centigrade and 2 bar pressure. Okay, so this is the feed, crude oil. Okay, this is the temperature and pressure of the crude oil. The steam temperature and pressure in the entire process are 400 degrees centigrade and 3 bar respectively. Now we have to use steam distillation. Okay, the column and process parameters are as follows. First, we have got the atmospheric column parameters. The column, that means atmospheric column, has 25 theoretical stages. It has a condenser. The condenser is of partial vapor liquid type because it condenses liquid, but it has methane also. Methane will not get condensed at that temperature, it will go out. So it is partial vapor and liquid type of condenser with temperature 60 degrees centigrade. Top and bottom pressures are 1.1 bar and 1.3 bar respectively. The distillate rate is 29,000 kg per hour. So the distillate is given. We have a reboiler. No, we do not have a reboiler. There is none. The feed is led to a furnace at 355 degrees centigrade and 2 bar pressure. As we have said that we have the option for the furnace to heat up our feed, and that feed will be given to the column. Okay, so the furnace is there at 355 degrees centigrade and 2 bar pressure. So the crude oil is given to the furnace, and that heated crude oil is fed to the atmospheric column. And here our valid phases are vapor, liquid and free water, because crude oil will also have some water component, so we have to get those water out through free water stream. The stripping steam, we have to provide 2500 kg per hour of stripping steam. And as we know that the stripping steam, it has a temperature of 400 degrees centigrade and 3 bar pressure. Okay. And we have 3 side strippers. What are the need for stripper? I have already said that we have to take out multiple components out of the atmospheric column. So to take out them, we have to use some strippers in between. Not only the heaviest key and lightest key. We have to take out individual cuts from in between. So the first stripper, it takes out naphtha. The second stripper is used to take out kerosene, and the third stripper is used to take out the light gas oil. Okay, and their flow rates are also given. Flow rates are heavy naphtha 27,500, kerosene 34,300, and light gas oil 76,000 kg per hour. Their steam flow rates are also given 1,500, 600 and 100 respectively. The strippers, they have the theoretical stages, 4 theoretical stages for the first one, 3 theoretical stages in the second one, and third one has also 3 theoretical stages. And the stripping, it occurs through drawing some liquid from one end and keeping it back. So that's how the stripping occurs, right? So one liquid comes bottom, another liquid goes higher. So that way, so it is drawn out and given it back. So liquid is drawn out from the 7th stage and returned to 6th stage. Like this circulation happens. In the second stripper, it is taken from 14th stage, returned to 13th. The third stripper, it is 20th stage and sent back to 19th. These are the pump arounds. I already said what are the usefulness of pump arounds. Pump arounds are required for taking out the extra heat from the column. So they are taken out, cooled, and sent back to the column. So the first pump around, it draws at 5th stage, return to 4th. Second one, drawn from 12th, return to 11th. Third one from 18th, return to 17th. The circulation rates are given and the return temperature also given. Obviously, we can expect that the stage 5 temperature goes higher than 107, so it cools and sends it back to stage 4. Similarly, stage 12 should have a temperature higher than 205, so it takes out the liquid, cools it down to 205 degrees centigrade and returns it to stage 11. Like that, third pump around also serves its purpose. So this is about the atmospheric column. Then we have a vacuum column. And here we have the vacuum column. You can see the specifications are similar. It has 11 theoretical stages. Here the condenser is partial vapor. We do not have liquid over here. Okay? Entire condenser is partial vapor. Having a temperature of 90 degrees centigrade, top and bottom pressures are given, 0.1 bar and 3 bar respectively. The distillate rate is given. Here also we do not have a reboiler. The feed, that means whatever is coming out from the bottom of the atmospheric column, that we are sending it to the furnace. And the furnace is maintained at 380 degrees centigrade and 2 bar pressure. The valid phases over here, they are also the same, vapor, liquid and free water. The stripping steam over here is 5000 kg per hour. So we are sending steam. Now steam temperature and pressure are not given. We have to use the same one, that is 400 degrees centigrade and 3 bar pressure. The side stream, there are 3 numbers. Now here we do not have a stripper, but we have a side stream. Side stream means we take out the streams from the stage 3 first size side stream. It is light vacuum gas oil. Then from stage 5 we take out medium vacuum gas oil, and from stage 9 we take out heavy vacuum gas oil. So we just take out the streams from there. And the product flow rates are also given, 5000, 5000 and 250 kg per hour. And here also we use some pump arounds, 3 in number. The first one, it takes out from 2, returns at stage 1. Second pump around, it takes out from stage 4, returns at 3. And the third pump around, it takes out from stage 9 and returned at 5. And there, the circulation rates are given. And the temperature change is also given. It is 35 degrees centigrade, 20 degree and 20 degree. Now, do not get confused with minus. Actually, we have to provide the information in minus over there because temperature change is given in minus. So, how much reduction of temperature is done? Okay. So, here it is minus actually. So temperature change is minus 35 degrees centigrade. That means whatever temperature that was there at stage 2, so that liquid is taken out, cooled to a temperature which is 35 degrees centigrade lower than whatever we have taken out. And that amount is being sent back to the stage 1. Okay. Similarly, in the second pump around, we take out the material from stage 4 at the rate of 120,000 kg per hour, then cool it down reduce the temperature by 20 degrees centigrade, and send back the material to stage 3. And the similar thing is done through the third pump around. Okay, so that's what our list of information that we need to solve the problem. Now, what we need to do over here? So the tasks. The first task is you have to calculate the temperature and flow profiles in the atmospheric column. Now, the temperature and flow profiles, you know how to do it. We have already learned in other examples or other lectures. The second thing is compare the calculated ASTM D86 curve of the atmospheric column products. So whatever we have taken out from there with the experimentally measured distillation curves shown below. Now you might remember that we had obtained light naphtha, heavy naphtha, kerosene, light gas oil through the atmospheric distillation column. Those are the products of atmospheric distillation column. So we will get this information, ASTM D86 curve of the atmospheric column products, that will be calculated in Aspen. But these are the experimentally found ASTM D86 data. These are the experimentally found information. Now what you need to do is you need to compare them with whatever you have obtained through Aspen Plus. Okay, so that's exactly what it means. And finally, you have to calculate the ASTM D86 curves of the vacuum column products. There are light vacuum gas oil, medium vacuum gas oil, and heavy vacuum gas oil. For them also, you have to do the same thing, right? So this is the total example that we have to solve. For that, let us go to the Aspen Plus domain.